Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back. I hope everybody's been doing well. And I just want to say I've got some exciting news. I've got a new microphone, so hopefully you can hear me slightly more clearly. We'll see. Anyway, so let's get on with it. I'm trying to keep these videos nice and short. Let's have a go. So we are talking about Newton's laws. So what I'm going to do is I'm going to attempt to answer these from the revision pack, and then I've got one more question to do, and that's that. So let's start. The first question says a brick is at rest on a tabletop. A spring is then attached to the tabletop to the top of the brick and stretched by someone pulling up on it. The brick remains at rest. Is the normal force acting on the brick greater than, less than, or equal to the brick's weight? And explain. Here's the tabletop. Here's a brick. So the first thing we need to realize is that the brick has a weight force, and there is a reaction force, what we call a normal force, acting on it. And these two are equal and opposite. They are equal and opposite. So let's say, for example, the brick is 5 newtons. Then this would also equal 5 newtons. Now, what the situation here is that we have a normal force, and now somebody decided to attach a spring and is pulling on it. The brick is still not moving, but now we have two forces. We have tension force from the spring as well as normal force. And they are both equal to 5 newtons. So instead of before, it was normal force equals 5 newtons. Now it's tension force plus normal force equals 5 newtons. So plus normal force is equal to 5 newtons. So that means what happens to normal force? It got less. Normal force reduced. So it's less than before, because now we have another force supporting it. Okay? Next, we have a parachutist who jumps out. So we've got an example here of a parachutist, a jumper who jumps out of a plane, and after an extended period of free fall, just a second, somebody's calling me, and we're back, sorry. So as I said, so a parachutist jumps out of a plane, and they're in free fall for a while. So why did they say that? Why did they say they're in an extended period of free fall? That's to say that they have reached terminal velocity. They're not accelerating anymore. They're not changing velocity. So to decelerate your fall, must the force exerted by you in the parachute be greater than, less than, or equal to your weight? Okay, so that's a tricky one. So you're falling down, and you try to determine, and of course there is the acceleration towards gravity pointing downwards, and you're trying to slow down. So what do you need to do in order to slow down? You need to counter that acceleration towards gravity in the opposite direction. So if you are falling downwards and there's g, you need to counter g with a negative acceleration. If we consider this positive, then you need to counter it with a negative acceleration, and that will slow you down. Okay? And another way to put it is, see, when you jump out of a plane and you open your parachute, okay, the force exerted on you by the parachute, that means the force that the parachute is holding, has to be greater than your weight. So it creates air resistance, which pushes against gravity, which slows your fall down. Okay. Let's try and work it out mathematically. Okay, so let's say the force from gravity is equal to mass times acceleration, and let's say you have a mass of about 70 kilos, and the acceleration of towards gravity, the acceleration will be 9.81. Okay, so now basically you have an overall force of approximately 690, 70 times 9.81, 70 times 9.81, which is approximately 687 newtons, right? Now, if I'm to counter this, let's say, for example, I open the parachute and the parachute creates a force upwards of about 1,000 newtons. This is what we call drag. Then we have a force downwards of 687 newtons and a force upwards of 1,000. That means the overall force acting on the parachutist, the person falling down, is going to be 313 newtons. And we know force equals mass times acceleration. If we have 313 newtons acting down and the mass is 70, then suddenly the acceleration is a lot less, which is 4.5 meters per second squared, as opposed to 9.81. Okay, so obviously this has reduced. So that's what you need to do. You need to have a weight force that is greater than your weight force. The force exerted on you must be greater than. So which one of them would be the correct one? A parachute can only exert a force that is less than the weight of the skydiver. That's not true. A parachute exerts a force exactly equal? No, because if it was exactly equal, they would continue to fall at the same rate. To decelerate, they must exert a force that is opposite. In fact, this is what's happening here. So this is negative 4.5 meters per second squared. Why is that? To counter gravity. Gravity is 9.81 meters down, and this is negative 4.5 meters up. So what is this going to do? It's going to slow the person down. So if they are moving initially at say, for example, 50 meters per second, or yeah, that's approximately correct. Let's say they're moving at a rate of 50 meters per second. At minus 4.5 meters per second, and let's say, for example, after 10 seconds, then their speed would be negative 4.5 times 10 seconds is equal to negative 45. The initial speed is 50 plus negative 45. Their speed, the final speed, would be 5 meters per second. So it would slow them down. Anyway, the option is C. Sorry if it's long and winding. Let's look at the third example here. What are we doing for time? 7.5 minutes. Inshallah, we'll finish before 20 minutes. 3 astronauts. 3 astronauts use their jetpacks to push on a satellite in deep space. Astronaut 1 exerts a force of 52 newtons in the positive x direction. I'm going to draw the satellite. Here's the satellite. And there's 52 newtons in the positive x direction. Astronaut 2 exerts a force of 35 newtons in the negative y direction. Astronaut 3 exerts a force of 74 newtons at an angle of 63 above the x-axis. Okay. Use a ruler and protractor to determine the approximate direction of the magnitude of the net force acting on the satellite. Well, I'm not going to use a ruler and protractor. If the satellite has a mass of 680, what is the magnitude of the acceleration? Okay. So instead of using a ruler and protractor, I'm just going to do it mathematically. And how do you do it mathematically? Well, the key is this guy here. The key is trying to work out the x and y components of this, which of course we use SOHCAHTOA for that. So we are trying to work out this component and this component here. Okay? So in order to work out this component, the opposite side, then we use sine 63 multiplied by 74. And that gives us 66 newtons in this direction. And then we have cos 63 multiplied by 74, which gives us 33.6 newtons in this direction. Now what do we do with that information is we add these. Now this is the y and this is the x, and this is the y and this is the x. Now we're just going to be careful with positives and negatives. So you can see that both x's are facing the same direction, so it's going to be 52 plus 33.6. So overall, that is what a new triangle looks like. We have 85.6, and then we have 66 that is positive, and 35 that is negative. Okay, so it's going to be 66 minus 35, which equals 31. Overall 31, that's positive. And now we can work out the new angle. How do we work it out? We use tan. 31 divided by 85.6, which is opposite over adjacent. Then shift tan. And that gives us the new angle, which is approximately 20 degrees. So we know the direction. We know the direction is at 20 degrees, but that's not what they're asking for. They're asking for the acceleration. How do we work out the acceleration? The rules haven't changed. Force equals mass times acceleration. So first we have to work out the force, the overall net force, using the x and y components. And then once we work out the force, we divide it by the mass and we get the acceleration. So we have 31 and 85.6. What do we do to get this? A squared plus b squared equals c squared. We're trying to work out c squared. So it's going to be 31 squared plus 85.6 squared. Square root of both of these equals 91. So this equals, the hypotenuse equals 91 newtons. Okay, now I have the force, which is 91. I have the mass. They told me the mass, right, of this satellite, 680 kilograms. I have the mass, I have the force. So it's going to be 91 divided by 680, which equals A, acceleration is equal to 0.13 meters per second squared. Now notice I didn't actually go through the boring steps and everything else. And that's kind of deliberate in a way. I want to give you the answer, but I also want to give you a chance to struggle a little bit with it. So what I want you to do is I want you to go through it. Okay, and if you do understand it, that's fantastic. Try and explain it to a colleague. Try and explain it to a classmate. The best way to know that you understand something is by explaining it to someone else, is to play teacher and explain it to someone else. Okay, how are we doing for time? We're at 13 minutes. Let's go to the last question. To give a 19 kilogram child a ride, two teenagers pull on a 3.7 kilogram sled with ropes as indicated in figure 5.24. So this is figure 5.24. Both teenagers pull with a force of 55 newtons at an angle of 35 relative to the forward direction, which is direction of the motion. In addition, the snow exerts a retarding force. That means it causes friction on the sled that points opposite to the direction of the motion and has a magnitude of 57. Find the acceleration of the sled. Diagrams make everything so much easier. Find the acceleration of the sled. Okay. Now obviously the sled is moving forward, but they are pulling at an angle. So what we need to do is work out the force A, which is moving forward. That's what we need to work out. We're not interested in the hypotenuse, in the force at an angle. We're interested in the force in the same direction as the movement. Okay? So what do we have? We have the mass of the child as well as the sled. We need both because they are together, the mass of the child and the sled. Hopefully you recognize that. That's the first trick in this question, is that you need to realize that it's the sled and the child together. That's the first thing you need to recognize. Second thing is, we need to work out this force A. How do we work out force A? Well, the rules of mathematics have not changed. This is the adjacent. If we look at the triangle here, we have the hypotenuse. We need to work out the adjacent. And remember, there's two of them. They're exactly the same. So here's what we have. We have 55. We have an angle of 35. We need to work out this side A. And if we work one, we can do both. We can just double it because they're both exactly the same. So how do we work out the adjacent? Cos 35 multiplied by 55. This gives me A is equivalent to 45 newtons. There's two A's. Why? This guy is pulling and this guy is pulling. They're both pulling. So they're going to produce 45 times 2, which equals to 90 newtons. Are we done? No, of course not. We have a pullback of 57 newtons. That means the snow is slowing it down by a factor or magnitude of 57. So it's going to be 90 minus 57 to work out the overall net force. It's going to be 90 minus 57, which equals 33 newtons. So the overall force acting on the child with the sled is 33 newtons this way. Are we done? No. No, we're not done. Again, we have to go back to force equals mass times acceleration. We have 33 newtons equal to 22.7 multiplied by the acceleration. So the last bit is now basically dividing by 22.7, which gives me the acceleration. Therefore, the acceleration is equal to 1.46 meters per second squared. Okay, as I said, the best way to do this is by doing it and then trying to explain it to someone else. All right, we have kept it at 17 minutes today. Okay, thank you. Over and out. I will see you in the next one, inshallah.